Welcome. In this lecture, we are going to talk about fixed point arithmetic and the concept of Q format. In fact, this lecture is the continuation of the previous lecture. In this lecture, we want to again consider the binary number system, and we try to link how this binary number system can be linked with a real voltage when we are dealing with an A to D converter. That is a gateway which represents a binary number and the analog voltage. Then what is the concept? How can we generalize such number system representation and equivalence between the analog voltage? How can we link with a generic form, so that we have to because in the FPGA implementation we will deal with different type of coefficient of the controller. So, how can we make a generic representation, that is called Q format? Then what are the rules for addition, subtraction, multiplication in Q format? And finally, we will take an example of arithmetic operation in Q format. So, if we go to the fixed point arithmetic, let us consider a 2 plus 2 bit number. Basically, it is a 4 bit number. So, that means in the 4 bit number, I can write something like this. That means I can write B3 into 2 to the power 3 plus B2 2 to the power 2 plus B1 2 to the power 1 plus B0 2 to the power 0. This is one way of the representation. Now, I can also write in this way, that means this B3 to B0 is that means we have a number which is B3, B2, B1, B0. And in this way, if we write a straight, that means nx in decimal, what we will get? So, it can vary nx decimal, it can vary from varies from 0 to what? What is the maximum number? This is like 8, 4, that means it is 31, sorry, it is 15, because it is a 2, 4. So, 0 to 15, that is varies between 0 to 15. So, if all are 0 bit, then it is 0, if all 1, it is 15. But we can also write another representation. Let us say, suppose we write B3 into 2 to the power 1 plus B2 2 to the power 0 plus B1 2 to the power minus 1 plus B0 2 to the power minus 2. Now, how is it coming? You can think the same number I just represented with a scaling factor. So, let us say we are talking about a scaling factor. A scaling factor. What is the scaling factor? That means I can continue the same number here, because we want to write the same number nx in decimal, the same number with a scaling factor. What is the scaling factor? So, here n scale is equal to 2 to the power 2, because if you multiply 2 to the power 2, actually these two are same, everything same. So, I took 2 to the power 2 out. Now, why it is needed? I am coming to that point. So, I would say this to be, this number I can say like a ny in decimal. So, ny in decimal is basically a scaling factor multiplied by nx, sorry, I am writing the other way around. So, it should be nx, it should be ny. And this scaling factor can be different. So, the beautiful thing here, as if I write in one case B3, B2, B1, B0, it looks like all like integer. In the other case, you see from here, from this point onward, it looked like a fraction. That means, in the other case B3, B2, B1, B0. So, that means in the first case, as if from this point or not decimal start, but there is no decimal, but here we have inserted a decimal concept here virtually. That means when you write about decimal number in the binary, in fraction, it will like a B3, B2 dot B1, B0. It is something like this. It is a dot, that means it is a fraction position here. But the fixed point will never see a fraction, it is just a 4-digit number, but you can either represent in this nx form or ny form. It is a notional concept. But the question is, why do you need so? So, let us go to that number and let us consider this ADC. Suppose this ADC, let us say we are talking about first unsigned number. So, let us say it is an unsigned ADC, or I would say it is in the format of straight binary. Assumption. So, this is an assumption. Okay. What is the minimum value? Let us say it varies between 0 volt and it varies between 2 volt. That means we are dealing with an analog signal where this is the analog signal is analog input and we are getting a corresponding output. Now, I want to write this data in such that I will get the quantized. So, last time what we did? We did that quantized VA to be what? The quantized VA we got, it is the V span divided by 2 to the power n bit multiplied by nx, that we have written. So, here this whole thing we want to write as if in terms of ny in decimal, right. So, this is in decimal ny. That means how it is possible? So, let us say what was our nx? Our nx is, it is a 4-bit number. This 4-bit number, it varies between B3, B2, B1, B0. And then what is nx? So, nx is basically, what is nx? Nx is basically B3 into 2 to the power 3 plus B2 into 2 to the power 2 plus B1 2 to the power 1 plus B0 2 to the power 0. Now, what is ny? Ny will be nx multiplied by, what is my V span? It is 2 volt divided by 2 to the power, what is the bit size? 4. That means, it will be nx into 1 by 2 to the power 3. Then how do you represent? So, I can represent this like B3 into 2 to the power 1 plus B2 into 2 to the power 0, right, 2 to the power 3, okay. Then B1 2 to the power minus 1, or it is divided by 2 to the power 3. So, it should be 0, sorry, minus 2 plus B0 2 to the power minus 3. So, this is my ny. What is the difference between this number and that number? What is the difference between this? What is the difference? What is the difference? The only difference is that the power of 2 to the power 3 whole thing we have multiplied with a factor which is 1 by 2 to the power 3, and ny is this, and this is called Q format. So, here it is like 4 Q dot 0, that means virtually there is no fraction. Here it is like Q, there is only one integer bit, all are fraction. So, it is look like Q1 dot 3. This is called Q format, where there is no physical, because you will only see B3 to B0 all like a number system. because you are only accepting data which only takes between all like a 4 different bit, and each bit can take only 0 and 1, that is it. But we want to represent how this output can be mapped to the analog voltage. So, for that Ny is nothing but your quantized Va straight away, and this is in the form of Q1.3. It is an unsigned number. In case of Q1.3, you know the first bit is the MSB. If all bit are 1, because first bit can take only 2 to the power 0, that means it can be 1. But if all other bits are 1, so that means it is almost close to 2. That means if you make all bit to be 1, it will be 2 to the power 0 plus 2 to the power minus 1 plus 2 to the power minus 2 plus 2 to the power minus 3. How much it will be? 1 plus 0.5 plus 0.25 plus 0.125. So, it will be 1 point, that first last digit will be 5, next 2 to 4 9, no, sorry, the next will be, so the next digit will be, so last the third digit is gone, then 2 plus 7 plus 1 plus 2 3 plus 5 8. So, that means if all bits are 1, then you are getting an quantized voltage is 1.875, because that means your analog voltage, let us say it is 2 volt, but you are getting a quantized voltage of 1.875 volt. That means there is an error of 125 millivolt, which is pretty large, may not be acceptable. So, you need to increase the number of bit size, so that you can reach close to 2 volt. If you increase the resolution, then this number will further come close to 2 volt. That means you take 6 bit, then you will get another point, another bit will come. So, like that way you will approach. But again we discussed that too many bits may not be acceptable. But what we understood from here, that instead of writing all the time the actual binary, we can write in terms of Q format, and there is a standard way, as if it gives you how to realize a binary number to a real world voltage. So, you can say in Q1.3 format, in this case is a real world number. For example, if you are getting a bit, that means let us say first bit is 1, then 0 0 1. Then in Q1.3 what is the number? So, it will be simply 1, that means 2 to the power 0 plus 2 to the power minus 3. That means it is simply 1 plus 0.125. So, it is 1.125 volt. That means this is a realization of this Q format. Okay. So, this is the concept of Q format. So, Qn dot m, that means n bits are integer, m bit are fraction, but it is again a notional concept just to map a real world number, but actual total number of bit size is n plus m. That means integer bit and the fraction bit, again it is a notional. But whenever you say Q format, generally we by default consider sign, because it is easy. So, what will happen for the sign? Let us say we are talking about Q2.2. So, Q2.2 means we are talking about a 4 bit binary. So, this gives you a 4 bit binary. Now, it can be two things can be possible. It can be straight binary, or it can be 2s complement. So, in straight binary, in all cases we will write B3. It is in the 2.2 format, right? B3. I am talking about the straight binary. Then what is that? Because we have 2 integer bit. So, 2 integer bit means the last bit must be 2 to the power 0. So, naturally this will be 2 to the power 1. Then B2 2 to the power 0 plus B3 2 to the power minus 1 plus this will be B1, then B0 2 to the power minus 2, right. This is for straight binary. Then what happen if, that means this is called straight binary, I would say unsigned number. But what is the signed number? It will be minus 1 B3 2 to the power 1 plus B2 2 to the power 0 plus B1 2 to the power minus 1 plus B0 2 to the power minus 2. Now, we are talking about this. So, the example is that if we take, let us say 1 0 1 0. In this case, what will happen? Unsigned number, it will be how much? The first digit is 1, so there will be 2, then third digit is 1, so it will be 2 to the power minus 1, so it will be 2.5, correct. What will be the signed number? Because the sign bit is 1, so it will be minus 2 plus 0.5, so it will be minus 1.5. Okay. So, that means minus 1.5. So, that means what is the, for 2.2 format in sign, it can take value between minus 2 to plus 2. In case of unsigned number, it can take 0 to 4, close to 4. I am not talking exactly 0 to close to 2, because there will be a quantization error. So, this is what is the cube format, and now onward we are moving with 2s complement. So, we are just talking about the second representation in this cube format. So, anything that we talk about, this number, it start with, let us say 2 point bit. So, this is like Q, what is that? 2.3 format, and we by default, let us assume we are talking about signed number. So, then n equal to 2, 3, so it is a signed number. Then as we discussed, first digit, so it will be minus 75, sorry, it should be negative, no, minus 1.2, minus sign is missing, it will be minus 75, because it is leading bit is 1, so it must be negative. Okay. Then what is the largest value of nx in this case? What is the bit size? Again it is Q 2.3 format. So, this is the general representation of Q n dot m, where n is the number of integer bit, m is the number of fraction bit. But in Verilog, we can write underscore. This is for the notional concept that we are distinguishing between the decimal and integer. But in Verilog, this underscore will be ignored, it will treat simply this 5-bit number. But we need to use proper cube formatting to make it consistent. This is a fictitious number, the first one is the MSB, then it is LSB. So, this is like Q dot format, minimum value. So, you can represent here MSB, LSB, and we have discussed. Now, we have discussed about Q format of a particular number, but suppose we want to add nx plus ny. Both are signed Q format, but they have different Q format. So, in one case, let us say this has Q 2.3, but this has Q, let us say 1.4. Then how do we add? So, we cannot add these two number unless we match their size. Without matching, we cannot. That means, first of all, even though both are 5-bit number, but we cannot simply add because they are not in the same format. So, we have to take for addition the integer bit, that means it is like a Q. So, here in this case n1.m1, n2.m2. So, we have to take max of n1, n2, n2 for MSB. So, what is the maximum? Here will be 2. So, you need to convert something like a 2 dot. Similarly, max of m1, m2. and max will be 4. Now, the question is, how can we convert this to this? Because if you remember this, suppose this is my nx. So, nx will be something like, how can I represent? Nx will be something like in 2 dot format, it is a sign number -1 b2 2 to the power, sorry, it is in the 5-bit number, sorry. So, it is a 5-bit number, so it will be b4 for this number, then 2 to the power, since there are only 2 integer bit, it will start with this, then b3 2 to the power 0, then b2 2 to the power -1, then b1 2 to the power -2, b0 2 to the power -3, because there are 3 fraction bits. Now, I want to convert, that means I want to make nx normalization. So, this is in Q 2.3 format, I want to make it 2.4. How can I do that? So, we can, this number will not change if we write the same thing minus, we maintain this 2 to the power 1, b3 2 to the power 0 plus b2 2 to the power -1 plus b1 2 to the power -2 plus b0 2 to the power -3 plus 0 into 2 to the power -4. It does not change. That means, now this normalization will look like b4, b3, b2, b1, b0 and 0. So, we have resized the data by padding 1 0 or adding 1 0, that means we are adding a 0 in the LSB. So, any data bit you add in the LSB with a 0, it does not change the number. So, this number will remain same. What will happen for this number? So, now this format is Q1.4 format, I am just talking about NY. So, how does the NY look like? Again there is a minus sign, it is a sign number we are talking about, and this is again B4, the first MSB, because the number is B4, B3, B2, let us say B dash, just to avoid any confusion, then B0 dash, B dash. Since there is only one integer bit, it will be 2 to the power 0, then B3 dash 2 to the power -1 plus B2 dash 2 to the power -2 plus B1 dash 2 to the power -3 plus B0 dash 2 to the power -4. Now, I want to represent this number because I want to add this. So, this becomes a 6-digit number. Now, this is a 6-digit number where this is the fraction bit and this is the integer bit. Here we are putting a line here, this is my fraction bit, integer bit. Now, I want to represent. So, I want to normalize y, again normalize, this is Q1.4 format, I want to convert it to Q2.4. How do you do? So, it is simply sign extension, that means again it is a sign number -1, I will simply extend that bit by 2 to the power 1 and rest of the bit I will keep it, that means B4 dash 2 to the power 0, then B3 dash 2 to the power -1 plus B2 dash 2 to the power -2 plus B1 dash 2 to the power -3 plus B0 dash 2 to the power -4. So, by adding the 0, if you calculate, mathematically you can show that this number remains same, because earlier this was the leading bit. Okay. So, now what we can do, so here as if that means if you take any number, that means this is called sign extension, that means a number which was earlier was B4, B3, B2, B1, B0, is same as another before you can consider in case of sign. Because what you are doing, you are adding another bit, which means with this number we are, because the second bit becomes, now that bit has gone, like, because there now minus 1 has come out right here. So, we are extending the sign bit. So, now this will become minus 2, then plus the other bit number. That means, what was this case? In this case, it was minus 1 before that bit plus the rest of the number. In this case, it will be minus b4 into 2, because one extra bit is coming, plus b4 plus rest of the number. Rest of the number means, you know what is this? It will be b3 into 2 to the power minus 1, all this dash, sorry, dot 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 dot, b3 dash 2 to the power minus 1 dot dot dot. So, this part is common. If you subtract, you say this number after simplification will again become minus b4 dash plus this number. So, it does not change. That means, in 2s complement we can simply extend the sign bit. So, we can resize this data by, we can increase the MSB, just simply extend the sign bit, and that is a common practice. So, the sign bit extension does not change the value. Similarly, the extension with padding with 0 in the LSB does not change the value. So, that means we can resize this data in this format. So, that means the maximum of this we have discussed, rest LSB paired with 0, rest MSB extended by MSB, example here MSB convert into 3.2. So, you extend this bit with sign bit, just now we discussed, another sign bit is extended. So, it remains same, because mathematically you can show that another minus plus will get cancelled. So, it will minus, it remains same. Now, if you want to multiply, you can multiply with two different formulas, does not matter. So, this will become, what will be multiplication? N will become N1 plus N2, M will become M1 plus M2. But since this already has a sign bit, this already has a sign bit, so resultant will have two sign bit. That means, there is one extra sign bit which is redundant, and I can simply discard the sign bit and I can do a left shifting operation and pad with a 0. That means, what I am mean to say, it consists of two sign bit. So, I can eliminate one sign bit, that means, I can do just shifting and then another LSB I will just pad with 0. So, that this will, that means, it should be plus 1 in order to keep the same q n dot m format. The data size will remain same, the value will remain same, but you are giving an extra headroom for the LSB, so that when you do the next operation, this extra headroom can be used for final resolution. So, it is giving 0, this is a sign bit, so you can discard. So, extra bits can be used for further processing for higher resolution. Now, we want to, why do we need all this? Suppose we are talking about the PI controller ADC. Let us say this is the error voltage and this is the error signal, and we need to process that. So, what is, if I take the first the proportional control, what is my proportional control? Suppose I am talking about a proportional control, where this is, I am talking about a Kp into Nx. Let us say Nx has Q 1.9 in sign. What does it mean? That means, this voltage varies between minus 1 volt to plus 1 volt, and Q 1.9 means the maximum value can be plus 1, close to plus 1, minimum will be minus 1. So, it is perfect. Now, the proportional gain I want to vary between 0 to, let us say, 3. So, I am taking Q to be 4.5. 4 bit means I will leave 1 bit 0, because proportional gain cannot be negative. So, 1 bit is gone, you have 3 bit. So, you can get up to 8 using 3 bit, that means almost close to 8. That means, if you keep all bit, that means is a 9 bit Kp. So, that means if you realize 0 and all 1, because there are total 9 bit 1, 2, 3, 4, 5, 6, 7, 8. First bit is 0, then all 1. So, this will give the maximum Kp. So, the Kp max will be approximately equal to 8. What is the Kp mean? Because we are not talking about negative Kp, it can be 0, all bits are 0. So, we can vary the proportional gain between 0 to 8, but at what resolution? So, this will be defined by this guy. So, resolution will be 2 to the power minus 5, that means 1 by 2 to the 32. So, it can be vary in the scale of almost 0.3, 0.03, 30 milli. That means, you can vary between 2.03 then 2.06 like that. Okay. So, by that way you can set proportional gain. So, now in the PID controller, the overall output will be n proportional plus n integral. So, the proportional part is clear, that means we got proportional. And what is the format of this guy after resizing? So, that means if we do not resize for the time being, it will be Q, because we know this N1, N2, M1, M2. So, it will be Q 5 dot 14, because 5 M1 14. So, this we got Q 5 dot 14. Now, we are talking about integral gain. What is the integral? We know that integral has integral previous plus there will be Ki into Nx instantaneous term. We know in actual equation, we know ui of n is equal to ui of n minus 1 plus Ki into V error n. So, something similar we are writing. But now, I want to understand what is the size of this guy. So, that means Ki, what we know Nx Q format is Q 1.9, because it is defined by this ADC. Then what will be the Q format of Ki? First of all, Ki cannot be negative. Now, in this it is talking about discrete time Ki, which is typically less than 1. So, it is reasonable that we can take 1.9, where it in positive sense it can be maximum 1, close to 1. If the first bit is 0, the MSB is 0 and all are 1, it will be close to 1, because we cannot take negative K. What can be minimum? Because this Ki will be fractional number. So, you have to give sufficient resolution in the right side. But after this multiplication Ki into Nx, so we are getting the resolution of 2.18. First of all, we need to resize, because there is an extra MSB here, sign bit, extra sign bit. We need to resize this, there is an extra sign bit here. So, this resizing is needed. We cannot simply multiply this, add these two, because they are in a different format, and we have discussed that how to resize it. First of all, what we need? You need identify the Q format. So, this will give an headroom. What is the variation of integral gain that you want? So, that we have identified. Okay, the next, the summary. That means, the summary is that n is the control that you want. What is the format? It has to be n proportional nominal, because we need to add in a proper format n integral nominal. What is the nominal? They must have compatible Q format, otherwise you cannot. So, that means we are talking about n dot m, this must be n dot m. What is n? What is m? That we will discuss. And this, if we add two number, it can be same, because in worst case what will happen? If both numbers are maximum positive, there can be overflow. So, we have to make sure, because if we add two binary number, 4-bit number, sign number, if both are positive, then there is a possibility of overflow, and that you have to detect, because in sign number is you have to be very careful about whether there can be wrapping error. If both are negative, there also you have to check. Otherwise, if both have alternative sign or they are not maximum value, then you may not have any kind of overflow. So, typically they are in the same number, but we need resizing of the data, because we got actual proportional gain in the format of Q. If you go back to our previous 5.14 and integral in the form we got 2.18, and remember, if you go back, this integral previous, if it is Q 2.18, this will be 2.18, this will be 2.18 in summary. Again, we are adding the two same size data, we should make sure that this data, and there is a high possibility in integral that it can saturate. So, when you go to the integral control, we will take care about the saturation limit. So, we need a resizing. Again, what will be the minimum size? So, the 5 has to be maintained, we cannot discard any MSB. So, we need to integral normalization, you have to make it 5.18, so that you extend with sign bit, 3 extra sign bit. And similarly, for proportional control, we need extend the Q 5.18, where remaining 4 bit will paired with 0. So, that means the sizing, that is 1. So, this is the addition of 2, and next you have to resizing the digital data to get the controller output should be in the form of, let us say. So, that means we got, let us say, what we got 5.18. So, we need to get 5.18 in this format. That means we got 5.18 is the controller nominal, but this may be too large, because what we will do with this controller output? So, this controller output has to be compared with a sawtooth waveform, but we have to check what is the resolution of the sawtooth waveform. So, we will go to that point. That means, we need also further resizing. So, first of all, we need resizing of the integral term, proportional term to add them, and then we need resizing of the Q to fit, because we have to compare with another signal, that is one. And secondly, we also need a saturation block, because there is a high possibility that integral will saturate and there is a sign. So, there can be wrapping error. That means, if you take a counter, let us say you are taking a 3-bit sign counter, what will happen? So, if 0 all 1 reach, the next you hit, it will be 1 all 0. So, this will be a wrapping error, and that can cause huge problem in your controller. So, you have to be very careful. We can put a limit here, so that it should not exceed. So, similarly for the controller, so you need to put a limit. So, in summary, we have discussed binary number with actual voltage, we discussed about the Q format, we discussed about how to resize the Q format for addition, subtraction, multiplication, what are the law, and then how to do arithmetic operation in Q format. Some basic idea we have discussed, that means processing of the resizing. That is it for today. Thank you very much.